Hi there, in this video we'll be talking about stress and strain, how we understand them and the fundamental physics behind them. And we'll be using these to work out how we can measure all sorts of different mechanical force, how we can actually sense this and then get it to our computer or our device somehow and work out what it actually is. Now we've got three main forces of interest that we could be measuring. One of them is tension, so when we're pushing things together and working out how much force is applied to them. That's a bit like those scales example that I showed you earlier. The next one's compression, where we're trying to pull things apart and work out how much force is applied as we pull things apart. And if we think about a building and the structures around the building, we can see that there's different forces at play there. There's forces of tension, for example, on the foundations and working out how much tension's on them. There's also forces of compression as we have maybe a cantilever beam that's under compression for part of it. We also have forces of torque, and we're looking at twisting forces, just like in this picture here. And we use, for example, a torque wrench when we're tightening up a bolt to work out how much force we're applying to the threads on that bolt and how much force is being applied as we turn it, so we don't apply too much and snap the thing off. Now, when we talk about applications for measuring these forces, there are tons of them, from weighing things like for cooking, but for weighing heavier things like materials as we're packing bags, cars, all sorts of things that we're going to be weighing as engineers or just as people in general. Sometimes we need to measure force when we're gripping so that, for example, if we're trying to pick up an egg or something soft, we don't destroy it as we pick it up. We want to measure how much force we're actually applying to the thing that we're trying to grab. We use them in infrastructure, putting strain gauges and measuring force on various beams and members, working out whether we're going beyond the load of whatever it's designed to be. Lots of different places we could measure force, and we want to determine force throughout the life of a building. And we also use them in condition assessment, doing surface testing and using things like penetrometers to work out, is something a soft surface or a hard surface? We can use them in things like earthquake detection, because these forces can induce vibrations and things, and we can measure those actual vibrations. We use them in cooking, for example, when we're trying to work out accurate amounts of different ingredients to put into recipes. I've mentioned the beams and struts. I've mentioned the torque wrench, where we can tighten things up and measure how much torque we're applying as a force to the nut or bolt that we're trying to tighten up. There's dam sensors like this one, so we can measure how much water we've got in here and what force that's providing on dam walls. All sorts of different areas we can measure force, and we need to measure force for everything from accurately selling something and working out how much of it there is, through the public safety of buildings and critical infrastructure. So let's move on then to the concept of stress and the concept of strain. Now, stress is a force per unit cross-sectional area that we apply to something. And strain is what happens as a result of that force that has been applied. So stress, we apply a force, and it's force per square meter or square millimeter or whatever it is. And then strain is the amount of deformation or displacement, the amount of movement we get as a result of that force that's been applied. These terms, we're not going to labor on them. It's something that we learned in year 12 physics and first year physics. So they're fairly fundamental terms, understanding how the stress and strain affect a particular material. And so we see the equations here. Our stress measured in pascals, which are newtons per meter squared. So it's force per unit cross-sectional area, is equal to our nominal force that we've applied in newtons, for example. And I've got the pounds there. We don't tend to use those pounds, particularly because we're dealing with SI units, not imperial units. But it's interesting to see the PSI, the pounds per square inch there. That's something you're probably familiar with, particularly when you're filling up your tires or something like that on your car. So it's something that's still used, but something that we're moving away from as we go into the SI area. And then divide by the area in, for example, square meters. Now, when we talk about strain, we have these nice stress strain curves where we see how the strain changes in a material based on the stress that's been applied to that material. Now, this strain is a unitless variable, so we don't have a unit with it, and it's essentially showing how much movement we're getting based on the stress that's been applied, how much deformation that there is. So here we have the change in length divided by the total length, or the previous length, the unstressed length. And that's what our strain, or epsilon, equals. We can also divide the stress by the Young's modulus of the material. Each material will have a different Young's modulus. You notice whenever we do either of those operations, dividing the change in length by the length, well, we're still working with meters and meters, or millimeters, or whatever it is, and dividing the stress that's been applied by the Young's modulus, they're both force per meter squared, or force per cross-sectional area. And so we're keeping the units the same, the units cancel out, and so we have this unitless value of strain.